In prior chapters, I shared details on how to integrate the inexpensive Argent weather station with an Arduino and how to realize telemetry of rainfall data using Adafruit's Feather Fauna. In this video, I'll summarize field tests for monitoring and reporting rainfall data over cellular networks to the Internet of Things from a hardened installation in Tucson, Arizona. To ensure accuracy, I'll review a method developed for determining rainfall depths using an analog gauge, and then use that method to test the accuracy of the tipping bucket gauge via reference to data posted to ThingSpeak. Briefly, just a quick shout out to the Arizona Department of Environmental Quality for purchasing the hardware demonstrated here and for giving me the support needed to realize and document these outcomes. Also, thanks to my kids who suggested some fresh ideas for the experiments presented here. Here's Joey, who helped me with my first rainfall simulation, as you'll see shortly. For those of you who just want to cut to the chase, here are the results of 10 tests for 4 different rainfall events simulated using this setup. Chapter 22 summarizes the code and circuit behind these tests, and as always, everything is posted to my website for your use under Creative Commons license. This is shared in the hopes you can help me improve what's been shared to date via comments posted to this video. In early March, I started witnessing some light rain. Given a busy schedule, I hadn't yet prepared a field installation for measuring an actual rainfall event, but I didn't want to let this opportunity slide. So I quickly collected all the components associated with my bench-tested circuit, placed them in a box, and located the circuit in my yard away from any vegetation or building walls so as to register an unbiased event. Given the late hour, I wasn't able to set up an analog gauge for comparison, but here's a summary of the first test. So you can see where I have the brick, a couple bricks holding up the tipping bucket rain gauge from Argent, and the electronics inside a piece of Tupperware. So we'll see how this performs tonight. Folks, you can see from my rainwater barrels that we had quite a bit of rain last night. I set this up a little late, about halfway into the storm, and sure enough, we got some good results. The first test shows promise, but in the absence of having another gauge nearby to test for accuracy, I can't really use this instrument to meet my employer's data quality objectives. Specifically, I'm concerned about the inherent accuracy of the tipping bucket gauge, as well as any issues that might arise during telemetry, such as drop data. In order to determine if the system is accurate, I need to compare results reported via telemetry relative to results reported by another gauge installed nearby. My next test was my first attempt at realizing the same during a subsequent rainfall event. It's March 18th, Thursday evening. You can see the water still draining off my roof into my barrels. And I actually came home early to set this system up. And it was posting to the Internet of Things. I was getting posts to ThingSpeak, but it was only posting battery voltage. So that suggests that there's probably something going on with my wiring. The fact that I've got this hooked up with those little DuPont connectors onto breadboards probably isn't the best way for a sustainable, repeatable experiment. So I've got to harden that system up a little bit. And you can see I have a little red LED that's flashing on and off pretty quickly there. So chances are good that this just isn't. Yeah, see. So this system's pretty sensitive to being moved around. So I'm going to bring this indoors and try to harden up the system so that hopefully get a better experiment going during our next rainfall event. So the idea here is to migrate the circuit into a weatherproof remote environmental monitor box summarized in Chapter 6 of this playlist. In the case of my agency, we have a few of these on hand, so I'll demonstrate how I went about integrating my circuit, including improvements based on lessons learned from existing deployments. With regard to the existing REM, let's first loosen these 2 screws so that we can remove the circuit mounted on the plastic baseplate. Next, we can approximate where the added components will be placed on that baseplate and attach them using standoffs as demonstrated in Chapter 6. Once everything was attached to the base plate, I tested the circuit to make sure everything was wired properly, as summarized in Chapter 22. Based on multiple tests conducted over extended periods of time, I did encounter one recurring issue having to do with missed tips, and found an issue in my code that was easily remedied. The first improvement in software was to eliminate any conditionals in my interrupt function responsible for counting tips. Since I'm debouncing using a hardware remedy, there's no need for this filter in software, and eliminating the same addressed intermittent problems I was having with missed tips. In addition, I also added code that would engage an LED on the microcontroller in response to bucket tips. During testing, this gave me visual confirmation that the associated interrupt function was being called by my tipped bucket, but the counts were being missed. The visual confirmation via the LED helped me determine that I needed to remove the conditional called out in the previous slide. Respective edits are now included in the code shared in the description of this video. Before replacing the circuit in my REM box, I'll take this opportunity to make a few improvements. First, I've discovered this terminal block on the solar LiPo charger is a point of weakness. I've observed the solar cable wires can detach if the watertight fitting that feeds the wire through the box becomes loose, or if the box is jostled for any reason. This will eventually lead to a dead battery. For some of our remote locations, that means we'll have to drive out to service the unit, which defeats the efficiencies we're trying to realize. An alternative for these particular boxes is to use a 2.1mm plug, which will fit with pressure into the receiving female plug on the charger. These can be hacked from inexpensive 9-volt battery connectors available widely on eBay. This improvement is particular to the boxes and bill methods summarized in Chapter 6 of this playlist, so use whatever method you feel is best to ensure a sustainable connection for your own deployments. To address this modification, remove any electrical tape holding together the wraparound conduit and cable where it comes into the box, and then loosen that fitting so that you can remove the associated cable. And here's that 9-volt connector with the 2.1mm jack I mentioned. You can cut off the 9-volt part of this assembly and strip the wires bare. And also take a few seconds to strip the leads off the solar panel cables so you have some fresh wire to work with. Before soldering the barrel jack leads to the solar panel cable leads, make sure to add shrink wrap on the barrel plug wires and also attach the watertight fitting on the solar panel cable prior to soldering. Once the leads are soldered and the shrink wrap is attached, this is what your completed connection should look like, ready for inserting into your box. Thread the barrel plug into the box, insert the watertight fitting, and attach the gasket with the nut on the male part of the watertight fitting on the inside of the box. The nut should slide easily over the barrel plug for this step. And then go ahead and tighten the nut. And on the other side of the box, tighten the watertight fitting, which should in turn take hold of the cable, making it more difficult to pull out. Remove the conduit fitting from the bottom of the box and angle your base plate and circuit into the box. Before you flatten out that base plate in the box, attach the barrel jack to the solar LiPo charger since it will be difficult to attach the same once the base plate is fully inserted. The base plate should fit in the box with the barrel jack casing pushing against the wall of the box. This ensures it won't accidentally pull itself out should the box get jostled or the solar cable be pulled for some reason. Resecure the base plate with the screws and protect any exposed wire with some heat-proof electrical tape. Okay folks, so I've gone ahead and I've mounted that little plastic board with all my tested electronics and back inside my box. You can see that I've got my watertight fittings that are reinstalled. They're nice and tight. This one's nice and tight to keep this from pulling out. I've gone ahead and I've used that hacked 9-volt connector to power up my solar LiPo charger. It's a little awkward the way it's fitting in here right now, but this is actually good. It's going to keep it from being pulled out, which is the problem that I was having with these wires coming into this little terminal header right there. So that's good. The battery is currently plugged in. I can turn on the Pro Trinket, and I can also turn on the power on the terminal block for the Phone a Feather. And if I hit reset, that'll start the algorithm for the Feather Phona to start listening to the tipping bucket rain gauge and transmitting to the Internet of Things. And if I want to turn it off, just turn it off right there, turn that one off right there, and we're good to go. Of course, if I'm going to store this for a few days, I can store it in the light. You know, I could actually put this outside to help that solar LiPo charger charge that LiPo battery. You'll notice that I have a thermistor that it's attached to the battery to keep it from charging if the battery should get too hot. You can also see that I have confirmation that the solar LiPo charger is actually working, because I've got this desk lamp that's on the solar panel right now, and that's causing that little charge indicator to come on. I went ahead and I reapplied electrical tape. Anywhere I had that red wire coming off the solar panel exposed and coming into the box, I replaced this standard electrical tape that isn't very good, doesn't hold up to heat very well, melts, kind of makes a mess. With this electrical tape that's actually, I'm informed, is used for automotive purposes. It withstands heat much better than the standard electrical tape. So hopefully that'll hold up much better to outdoor conditions, keep it from melting and making a mess all over the box. And my real reason for doing this is I just want to hide that red wire as much as possible. I'm going to add a little bit more right here because I don't want it to attract rodents or anything that might decide to chew on that. So it's just a matter of hiding it and also protecting it from sun. You know, UV can probably cause that wire casing to dry out and to crack. So that's pretty much it. Okay, so here's the hardened setup, the REM box that I just demonstrated the build for. You can see it's been zip tied to this old trellis that I had in my backyard. I've got my analog gauge nearby. I've zip tied that to a piece of PVC that's sitting in another piece of PVC so I can easily remove it and drain it as needed. And then of course I've got my tipping bucket rain gauge. And yes, I probably should lengthen this wire a little bit so it's not hanging like that. But for the purposes of just generating a test, I think it'll be okay. Hey folks, it's Friday, March 27th, about 8 a.m. I just opened up the box and reset the trinket so that the counter would reset on the tipping bucket rain gauge, given that we have some rain. Not much, but the skies are cloudy, and hopefully we'll get some accumulation and we can test the accuracy and the telemetry on this little box. And unfortunately the rain did not last very long. Things dried up pretty quick, as you can see. Regardless, I did reset the trinket, which is what's keeping track of the counts on the tipping bucket rain gauge, and I'll show you next what that looks like on ThingSpeak. And something kind of cool that I don't see very frequently is rain, or maybe that's even snow, falling on Mount Lemmon in real time. So that's kind of neat. I wish some of that would come this way so that I could test this, but I think I'm going to come up with an alternative plan for testing, given that the sky's pretty much cleared up around here. Next, I'll review a method developed for determining rainfall depths using an analog gauge, and then use that method to test the accuracy of my tipping bucket gauge via reference to data posted to the Internet of Things. This will help me capture the total error associated with my tipping bucket gauge, should accuracy and telemetry be a factor. Initially, it occurred to me that I could just pour the volume of water for a given rainfall depth from the analog gauge into the tipping bucket gauge and then compare the results. However, since rainfall depth is normalized by the collection area for each gauge, and since each gauge has a different collection area, I'll need to develop and test a simple method for precisely measuring water volume and converting that volume to depth for each gauge. From this point forward, I'm going to work in metric units, since it will make things easier for converting between volume, mass, and rainfall depth using these recognized relationships. Let's start with this analog gauge. The opening of this gauge measures 6.4 centimeters by 5.8 centimeters. That means that the total area of our storm that's intercepted by the gauge is 35 square centimeters. In order to determine the depth of rainfall, the markings on the gauge are calibrated to divide whatever volume of water enters the gauge by this cross-sectional area. This allows us to read the depth of rainfall directly from the gauge. In regards to our method for simulating a rainfall depth, let's say I want to calculate how much water to add to the gauge to yield a 5 centimeter storm. Intuitively, I'm going to want to measure a given volume of water, but eventually I'm going to need to convert that to units of length. In this regard, it's very convenient that 1 milliliter of water is equal to 1 cubic centimeter, which gets me closer to my desired unit. To convert volume to length, I can divide the respective volume of introduced water by the intercepted area of my gauge, which is 35 square centimeters. This will yield my rainfall depth in centimeters. And here's my equation for realizing my desired rainfall depth, where I'll need to solve for x. This is that same equation, solve for x, which indicates I will need to collect 175 cubic centimeters of water to yield a corresponding rainfall depth of 5 centimeters. That's a very specific volume of water, and my measuring cups aren't graduated in cubic centimeters. I might have a measuring cup that is graduated to milliliters, which is okay for preliminary tests, but probably doesn't carry enough precision for our ultimate goal. So how can I measure this out without access to expensive and precise laboratory glassware? One way is to consider the density of water and then use weight to back out the associated volume using a cheap kitchen scale. These scales are accurate to about a gram, which translates to 1 cubic centimeter. So this instrument is probably a little better for our purposes. Given that the weight of 1 cubic centimeter of water is 1 gram, I know that my target 175 cubic centimeters of water will weigh 175 grams. So if I weigh 175 grams as determined by my scale, and then introduce that mass into my gauge, it should report 5 centimeters of depth, assuming my approach is valid. So let's give it a shot. Okay, this is my son Joey, and he's going to help me with this experiment. We're going to test the accuracy of my method for determining how much water I have to add to a tipping bucket rain gauge. We're going to start with the analog gauge first. So here we go, Joey. So what do we do with our setup here?
We put it on the scale and then hit tare.
Well, what does that do?
It levels it out so it's a 0.
Uh-huh.
And then get that dead bug thingy out. You can put this in there and try to get it to as close as 100 as you can. So
let's do 175. We were practicing on 100, but let's see if you can get to 175. Oh, that's a lot. Keep going. Okay, you're pretty close. You want to use the oh, you're so close, Joey. You're so close. What are you going to do now? There you go. Perfect.
75.
And now we're going to go outside and we're going to put it in the analog gauge. Come with me. We're going to come up to our analog rain gauge. I think that's a little too tall for you, Joey. Let me grab a chair, okay?
I got it, Dad.
You do? Okay, are we ready to test it out?
Yeah.
Okay, go ahead and pour it inside our analog gauge.
Ah!
You can pour it all in there and not worry about it one bit. Make sure we get every last drop out there. Okay, there are a few drops in there, but we're good. Let's see how we did. Let's see. We're right at 50 milliliters, actually just a hair under, but close enough to demonstrate that, that the method that we're using to use weight to check the accuracy on these instruments is valid. Nice job, Joey.
Thank you, Dad.
Right on. Now that I have a proven method to convert mass of water to volume and depth, I can use that same method on my tipping bucket rain gauge. Here are a few more conversions we'll reflect moving forward. For this particular gauge, we have a constant of 0.011 inches per tip that is reflected in our code for reporting total inches to the Internet of Things for a given rainfall event. However, we're going to fall back on metric units again since these are easier to work with. So we'll use the metric constant for calculating tips. Let's first measure the capture area for the tipping bucket rain gauge. It measures 11 centimeters,
by 5 centimeters, giving us a total area of 55 square centimeters. The next two slides summarize the same approach for calculating the required volume to introduce into the instrument based on our success with the analog gauge. Giving us a total volume of 275 cubic centimeters for the same depth of rainfall, which translates to a mass of 275 grams that we can weigh out on our scale for testing the gauge. As a quick check, if we compare the cross-sectional area of the tipping bucket gauge relative to the analog gauge, it makes sense that we'll need a larger volume of water for the tipping bucket gauge to register the same depth of 5 centimeters, so far so good. In order to determine the total number of tips for translating the 5 centimeter depth, we'll use this constant reflected in the documentation for the gauge. For a 5 centimeter depth, we'll need a total of 179 tips. So we'll add that to our list of conversions that we can reference in a spreadsheet for tracking how well our tipping bucket reports relative to a fixed volume or mass of water for a given depth.
Okay, folks, so I'm going to do the same experiment this time with the tipping bucket rain gauge. This time I'm going to need to measure out 275 grams of water, and that mass of water should yield 50 millimeters or 5 centimeters on the tipping bucket rain gauge, calculated from a total of 179 tips. It's hard to talk about this and measure this out at the same time. Joey was better at this than I am. Okay, that's pretty close. There we go. The bucket. Check the video. I lost count while I was doing that, and see how many counts we had, or how many tips.
So for this particular test, I realized a 37% error relative to predicted tips. I did try this several times over and confirmed that the issue probably is that I'm overwhelming the tipping bucket gauge given the high flow rate, so I'm going to need to slow things down a bit.
Okay, I'm going to try this again, this time using a pipette to control the rate that I'm introducing water into the tipping bucket rain gauge. I have a feeling that I'm overwhelming the bucket, and that might be having an impact on my results. So here goes. This is going to take a little while. Each one of these is going to be about 11 milliliters.
So for this particular test, I realized a 21% error, a little bit better as a result of a slower flow rate, but still not really representative of what I'd probably encounter in a typical storm. So I'm going to have to slow it down even more.
All right, so this was a setup I developed to see if I could create something that would better approximate a rainfall event rather than me just pouring water into that gauge. So this is a little bit gentler in terms of engaging the bucket. I'm not overwhelming that bucket. It's tipping only when it has to, so I should get better results going about it this way. And all this is currently being recorded to ThingSpeak, so I should just be able to go to ThingSpeak and check it out there, what the starting and the ending tips were for this simulated rainfall event.
So for this particular test, I realized a 2% error relative to predicted tips. So I think I have a design that will allow me to repeat the experiment several times over to get a better feel for the accuracy of my setup. Next, I'll go over the details of a spreadsheet available in the description of this video for summarizing the test results. In this spreadsheet, I first specify the depth of rainfall being tested, and then the depth of rainfall reported via telemetry by the setup in order to calculate the percent difference. I then do the same calculation for measured tips and record whether telemetry was successfully captured. And here's the results of the first 8 tests for 3 different storms selected at random. But what if I want to determine the accuracy for a typical storm I might witness in Tucson? To do this, I can bring up NOAA's online precipitation frequency data server, select a latitude near or on my point of interest, and request the associated precipitation frequency table and select a storm of my choosing. For my location, I'm going to select a storm with a duration of 30 minutes that has a 50% probability of being exceeded in a given year, which is the same as a 2-year return period storm. And here are 2 simulations added to my table reflecting that specific return period storm. Based on these results, I can conservatively say that my telemetry setup with an Argent tipping bucket rain gauge should report within 5% accuracy for winter storms. Factors that may be contributing to error are summarized in this table, which are independent of the gauge and telemetry setup itself, suggesting the accuracy would probably be higher for a formal deployment. Finally, here's the telemetry that's been reported since I completed my simulated tests about a week ago. This demonstrates that the instrument is consistently maintaining communication on a 10-minute reporting interval while it waits for its next rainfall event, details of which I'll post to this channel when it occurs. So one challenge I might have with this setup is in actually capturing the intense rainstorms witnessed where I live during our summer monsoons. As demonstrated, it's possible the instrument can become overwhelmed during these events. I won't know for sure until we actually measure one of these storms, but it's certainly something to keep in mind. Having said that, there's always the possibility of adjusting the tipping bucket constant in your code to compensate for underestimating events as a result of the buckets becoming overwhelmed. This isn't an ideal solution, but it might get you a little closer to reality. I suspect intensity is the reason why the Walnut Gulch Experimental Watershed uses instruments that approximate accumulation using weight rather than tipping bucket counts, since weight will give you the same depth independent of intensity. Well, I hope you enjoyed this video, and if so, please consider giving me a thumbs up, and please don't hesitate to submit comments on how I can make this project better moving forward. Subscribe for updates. Thanks.